Okay, so I'm very happy to be here again, and I'd like to thank Jan and Piotr for all the hard work they must have done. And I'd like to say that I'm going to take out points from whoever arrives late. I'm kidding. Okay, so I am going to talk about mostly measurable pseudo-Anosov maps and this. And this generalization, this 2D analog of the Miller-Thurston theorem, but then I had to put inverse limits in the title in order for them to invite me here. Okay? So, anyway. So there it is, and I'll say something about inverse limits at the end. Just to. Okay, so here's the plan. I'll say a little bit about this needing theory of Miller and Thurston, but I'll say just enough, just a statement of this theorem that I'd like to kind of generalize, and then the talk is more about the definition than anything else. So I'll say what this definition of measurable pseudo-Anosov is, and then explain why, generalize, well, so there were pseudo-Anosovs introduced by Thurston, and then I sort of, generalized this and introduced this concept that generalized pseudo-Anosovs, and I'll say why, sort of, they're pretty good, but they're not good enough. So, and this is like, 15, 20 years ago, and I'll say why it is that it took this long for us to come up with the right what I hope will be the right generalization of this theorem, and because the measurable part in the pseudo-Anosov definition here is what I think will allow for the correct analogous theorem in 2D. Okay, so then I'll state this theorem, or it's not a theorem at this point. It's a conjecture, but I think it's an attainable conjecture. And then at the end I'll justify my being here and talk about inverse limits a little bit. Okay. All right. So let me just say a few words about 1D dynamics. So the dynamical study of endomorphisms of the interval is being very much studied for a long time, and this family here in particular, the quadratic family, was extensively studied, and Michał Mizurewicz, who was the person I came here for the 60th birthday 10 years ago, was one of the champions of proving results about many important and very nice, beautiful results about endomorphisms of the interval. So here's a picture. I realize that the graphics is not excellent, but then again, I stole it from the web, and this is a picture of this family here for the parameter mu increasing from 0, and then it increases in the hump here, gets all the way to the top when mu is equal to 4. Okay. All right, so what do I want to say about this family? So there's so Miller and Thurston sort of produced this manuscript that for a long time was unpublished, but it sort of sorted the topological theory and several other things about multimodal, including the unimodal. So these are called unimodal because they go up and down only once, only one critical point. But this so-called needing theory of Miller and Thurston applies to any multimodal map or any multimodal family, and a multimodal family is a family that has finitely many turning points, as they're called. And the needing theory sort of explains its topological dynamics. It proves lots of nice theorems about it. But the one so I can't go like this, or else I start screaming. Sorry. So the one I want to talk about is this semi-conjugacy to a piecewise linear model with constant slope. Okay? So let me just say a few definitions here. So you say that if a map is multimodal, like this one here has 1, 2, 3, 4, 5, 6, 7 intervals where the map is monotone, then you count the number of monotone intervals of the iterates. Okay? So that's called the lap number. So you count this number of monotonicity intervals of all the iterates, and then it's not very hard to show that this limit here, if you take the nth root of the nth lap number, this limit exists. Okay? And this is called what is it called? The growth rate, maybe, of the interval. It's denoted by S of f. And one of the several things that they prove in this paper states the following, that if you start with any multimodal map, for example, you start with some unimodal map here, choose a parameter in the unimodal family, and assume that this growth number here is bigger than 1. Okay? So then there exists a unique single multimodal map with the property that it's piecewise linear, but more than piecewise linear, it has constant slope. I mean, the slope is either plus S or minus S, where S is this growth number here, and a continuous surjective and monotone map, age from the interval to the interval, which semi-conjugates the multimodal map F you started with to this piecewise linear model with constant slope. Okay? So it's saying that, down here, the growth number is 1, but as soon as you start growth number bigger than 1 somewhere around here, then the semi-conjugacy kicks in, and then you produce a map in the so-called tent family. And this tent family here, so since I actually mentioned it, so here it is. Okay, so the tent family is got, and the point about the tent family is that it's piecewise linear, but the slope with which it grows and goes down is either t or minus t, right? There's a minus sign there. Okay, so it's absolute value of the slope is constant. Now what I drew here, so the story is this. So this is a good drawing because Toby drew it, right? So, but after having asked him to draw this, I couldn't possibly ask him to make another picture, so I stole it from the web, and then it's a bad picture. Sorry, but anyway, so that's a nice picture. So, these are these tent maps, but I'm restricting them. So the picture. Oops, sorry. The picture here is different because I'm actually restricting these maps to a smaller interval in here, where actually the dynamics happens. Okay, so all points that are very close to the left here, they eventually, so as you map them, they eventually fall into the smaller interval and stay there forever. Okay, so oops. So the interval is this. The important interval where things actually happen, dynamics actually happens, is between the first iterate of the critical point, which is C in the middle here, and the second iterate. Okay, so that's why. So the first image is here somewhere, and then you come down and you end up cutting it some interval in the middle. And what you parameterize is the larger t is, the further down the leftmost point is here. And this map that goes all the way from the bottom to the top and back, that's t equal to 2. Okay. Anyway, so that's what I wanted to say about dimension 1. So let me say a few words about dimension 2. So for example, the Henon family. So the study of two-dimensional diffeomorphisms goes back through a long way, at least, the Poincare first return maps and such things, and then Birkhoff, and then many people have studied two-dimensional dynamics and diffeomorphism in dimension 2. And the Henon family in particular is this family here, which is a generalization, or it's a sort of a fattening of the one-dimensional unimodal family. Okay? So you just add this minus by to the formula, and all of a sudden you get an example of a two-dimensional family of homeomorphisms. Okay? And if b equal to 0, then you're back to the quadratic family. So b is supposed to be thought of as a thickening parameter. For b small, expect to see, much of the quadratic family, behavior appearing again. And anyway, so this family is also being kind of responsible for the sustenance of several mathematicians, including me, for many years. So here are some pictures, and I was thinking of showing even more pictures with another nice program, Toby. So here are pictures of, so there's a fixed point here which pretty much always exists, and there's another one in there. And as the parameter A, or the parameter mu rather, this parameter mu increases, so you start from having just these two fixed points, and then these stable and unstable manifolds start to become more complicated, and they start intersecting, and then as mu, for mu large enough, you have this pattern of intersections here, and this is a full horseshoe. Okay, so it's got a full two-sided two-shift, and there is sort of where the story sort of ends. You can't produce any more dynamics with this formula. Okay, this is, I guess, as I stated it, is a theorem of Bedford and Smiley. So I brought a program, again, due to Toby, because I can't program to save my life, I'm afraid. So there it is. So this, oops, I'm sorry, okay, so I have to try again. Sorry. Okay. Oh no, sorry. Stop. Okay. So that's what you see. So this here is the A-B parameter, and that's where the mouse is, and well, I don't know exactly what the values is, but this is A and that's B. So as you, so that's the full horseshoe, but as you push, A, oh, sorry, it's not A, it's A in the usual Hanon parameterization. This is mu in my formula there, okay? So then you start seeing that, there's a first tangency happening somewhere there. And then as you keep pushing, you start getting homoclinic intersections, and then you see a picture that's sort of like the one I had in the middle there. And then you keep pushing, oops, and then you lose everything. All right. So here I think, right, what it's plotting, it's plotting both. Anyway, there are two fixed points here, one here and one here somewhere, and somehow, I don't know. Well, anyway, so this is just part of the entertainment. I hope you were duly entertained. And let me go back to my transparencies. Okay, so and the point about this family is that we know, kind of, we understand this, we understand that. And we understand some, of what goes on for parameters in between. But, in the unimodal situation, there's a very complete, very beautiful, and in particular, the kneading theory of Milner and Thurston explains all of the topological dynamics that happens between node dynamics, this and a full horseshoe that happens for mu large enough. Okay, so in dimension 1, everything is sorted. Everything is explained, in particular, about the topology of these things. In dimension 2, these maps have been around just about, for as long as the unimodal, as the quadratic family, and yet we don't really have much of a clue of what goes on in the middle here. People have proved several, nice theorems, but we don't really understand, have a global understanding what happens so how dynamics kind of builds up in this family as you pass from no dynamics to a full horseshoe. And I've been saying this, every other talk I ever given in my life, I say the same thing because it still stands like that, right? Okay, so what I'm going to talk about today is I'm going to propose a theorem that's an analog of this theorem here, of Milner and Thurston, and to try and say that if you have some sort of two-dimensional map, there's no multimodal map in dimension 2, there are no critical points, there are no lap numbers, there's no going up and going down. It's a point that has to be dealt with. But anyways, for some class of maps or for some type of with positive entropy, so this growth number here is related to the entropy, there is some way of semi-conjugating to a model which is piecewise linear with constant slope. Okay, so let me say what I mean by that. Okay, so what I mean is that, well, we want to find some semi-conjugacy to some nice map. Okay, but being nice is something that has to be defined, and this definition is sort of what this talk is all about. So, and in this piecewise linear, so if saying piecewise linear is a bit sort of misleading because it's not just the piecewise linearity that's the matter here, it's the constant slopeness that comes, that's important, because you could say, well, you could study the Losey family, which people have, right? So there's Japanese mathematician Yutaka Ishii has proved, the so-called pruning front conjecture for Losey maps. There's, Sonia, are you going to talk about Losey? Okay, so Sonia is going to talk about Losey maps. That's not what I'm going to talk about. Okay. So the piecewise linear maps I want to talk about have constant slope. Okay, but I'll have to explain what I mean by that, okay? So here's a list of, three properties that the one-dimensional piecewise linear maps with constant slope have, which I want to keep, okay? Well, so they're, the piecewise linear maps are linear. That's a good beginning. And they're expanding at all points, right? Except at the finitely many points where it's, it breaks. And the expansion factor is always S, okay? So the topological entropy of the piecewise linear map is log of this expansion factor. And the periodic points are dense. Okay? In this interval where the dynamics happens, okay? All right, so this is what I'm gonna, try and use as my guiding sort of properties that I'd like to. So here is a definition which has these properties, okay? So Thurston introduced the concept of pseudo-Anosov maps in his classification of isotopy classes of surface homeomorphisms. Okay, so if you look at the surface and you look at the homomorphism of the surface, you could think about its isotopy classes. That is, you allow yourself to vary the map by homotopy, and you consider all maps in the same homotopy class the same, and you could try and classify this for whatever reason. And Thurston had good reason to want to classify those because he was studying three manifolds and suspension three manifolds associated to surface homeomorphisms, or a very kind of nice class of three manifolds to study. So he needed to understand, which three manifolds, he wanted to understand which fiber three manifolds had hyperbolic structures, and then he came up with this classification theorem for isotopy class. Right, so the three manifold depends only on the isotopy class of the map the surface map you start with, so he needed to understand isotopy classes, and he proved this theorem that classifies isotopy classes into 3 types, right? They're either finite order, that is, they come back to the identity after finitely many iterates, or they're reducible, you can kind of cut out a few curves and look at the simpler surface, or they're neither of these 2, and then they're pseudo-Anosov. And these pseudo-Anosov maps have some properties. So pseudo-Anosov map is a specific map. I'll give a definition in a second, but they have some nice properties. So in particular, there's a number lambda and a Euclidean structure on the surface. Okay, so the surface, the model, for the pseudo-Anosov, if you have a pseudo-Anosov isotopy class, it has a representative map, okay? And this representative map has the property that its surface where it happens, where it acts, has structure, and this structure is an Euclidean structure aside from finitely many points. Okay? And with respect to this, some cone points, and with respect to this Euclidean structure, the map is linear. The pseudo-Anosov map is linear, and it expands one of the directions by the factor lambda, and it contracts the other by the factor 1 over lambda. Okay? So the topological entropy of the map, the pseudo-Anosov map, is log of lambda, this expansion and contraction kind of rate, and periodic points are dense on the surface. Okay? So I'd like to propose these as the piecewise linear sort of models that we should kind of consider. Well, except, okay, so let me give a definition, maybe. Oh, anyway, so let me say quickly what. So you can generalize this definition a little bit. So in Thurston's definition, we allowed only finitely many cone points, but you can allow accumulation, finitely many accumulation of cone points. The definition is the same. So you define a surface homeomorphism. So this is a compact surface, say. It's a generalized pseudo-Anosov. So generalized is I'll explain in a second, but the definition is this: there's a finite phi invariant set sigma, which is the set of accumulations of singularities, but you require them to be finitely many of them. And then there's a pair of foliations. So in this pair of foliations look like regular transverse foliations everywhere, except at some points, which are special, and they have these special forms, or anything with more separatrices, and a number lambda such that the map contracts one of the foliations, or there's a measure, a transverse measure on one of the foliations which is contracted, and the other one is expanded by the same factor lambda, so the other one is expanded, and that's the map. The map squeezes one of the foliations, stretches the other, and kind of wraps things around. And the singularities might accumulate like they do here. So for example, you might have an accumulation of singularities, but if you don't allow accumulation of singularities, if you only have finitely many singularities, then you have exactly Thurston's definition. Okay? So Anosov is the Anosov on the torus. The pseudo allows finitely many singularities. The generalized pseudo-Anosovs allows infinitely many singularities with finitely many accumulation points. Okay? But but this definition, well, anyway, so this is a definition. Oh, so that's an accumulation of singularities. Okay, so as I said before, I think that this is the correct, concept of a two-dimensional map which is piecewise linear with constant slope. Okay? Why? Because the surface has this structure with respect to which you can talk about linearity, and then the map is linear, but not only is it linear, it's linear with constant contraction and expansion properties, rates, rather. Okay? But the problem with the previous definition is that it does not account for all the maps that we need. Okay? The problem is that, so this definition here, somehow it has built into it, the fact that I'm only allowing finitely many accumulation points, has built into it the fact that these maps have finite Markov partitions. And having a finite Markov partition is bad for what our purpose is here, because finitely many finite Markov partitions means that, up to topological conjugacy, these maps are countable. Okay? They're finitely many things that you sort of somehow map ones over the others. This is a countable set of maps. Okay? And a countable set of maps won't do the trick, right? I mean, so if you think about the 10th family, there are uncountably many maps because it's a real parameter that varies. Two or something. It's a real parameter, right? And every slope is a slope. Okay, and their slope anyway. There's uncountable set of slopes of piecewise linear maps, and this the generalized pseudo-Anosov collection of all maps, the family of maps, is a countable family. So it's not the whole thing. Okay. So in this work that Phil Boyle and Toby, there's a misprint, a typo here. And Toby is the king of non-typos. I read his thesis. It's a 200-page, and there's not a single typo. Never found one. Okay. So anyway, so he's going to kill me. I'm sorry, but you don't tell him. So I'll stand here because this is being filmed. Okay. Okay. So this is joint. You have to edit the tape. Okay. You can't? Shit. Anyway, so this work with Phil Boylan and Toby, we sort of came up with this definition. Oh dear. This is the end of the talk, is it? I have 2 minutes to finish? Oh, okay.
Half an hour to fill.
Okay, to fill. Okay, so here's the definition, okay? So, again, start with a closed, compact, no boundary surface. So a homeomorphism is going to be called a measurable pseudo-Anosov map. And I started, some of you, or maybe all of you, have seen this definition before in Lumini, and I had some cute name for this, and Fabio kind of suggested measurable. So a measurable pseudo-Anosov map is the following: is a homeomorphism of this compact surface for which there is a Borel probability measure which is invariant, and this Borel measure has got to be positive on open sets and on atomic. There are these two mu measurable foliations. Okay, so before I actually meant foliations, except at some special points where I explained exactly what the behavior was, right, with those pictures, and I allowed some finitely many accumulations of those singularities. So that was kind of describable in a sort of neat kind of way. Here I'm saying mu measurable foliations. I'll say in a second what I mean by this. But these two measurable foliations are phi invariant. And these mu measurable foliations on top of that have these holonomic invariant transverse measures. Okay, you can say what the distance between two leaves are, right? Just like you could in one of these plaques, you can kind of, if you look at the transverse arc, you can measure its size. Here too, you should be able to measure the distance between two leaves in a flow box, except that you don't have flow boxes. Okay. So there are these two measures, mu u and mu s on these transverse measures on the foliations, such that the original, the first measure here I said was invariant and existed, was non, etc. So it is the product measure of these two measures on the foliations. Okay, or if you want, you can disintegrate the measure mu into the two foliations to produce these two holonomic invariant measures. And then the definition is just before, the action of the map on the unstable measure is that it divides it by lambda, and the action on the stable measure is that it multiplies it by lambda, where lambda is this one, expansion and compression kind of factor. Okay? So this is the more general definition. So let me say what the words meant. So a mu measurable foliation is just a partition of this of the surface, or a partition of a full measure set rather, into one manifolds. Okay, so that's all there will be to this. And two such are transverse if they're topologically transverse on a full measure set. Okay. So in order to define no, definitely not. Yeah, that otherwise would be sort of back where we started almost. No, anyway, no. So what? Well, full measure one leaf, I find it unlikely. Right? Well, I mean, typically here, what so the singularities are going to be dense, right? But you don't have charts, right? But you can still talk about two arcs being transverse, right? Leaf-wise, yeah. Okay, so then you define what holonomy and everything happens actually. So the definitions, you have to be using these boxes, right? I mean, boxes are not charts; they're just boxes. And what a U-box is, let's say, it's a box with unstable arcs. But so a U-box is something like that. Okay, a U-box is a collection of leaves that are like that. And I'm not saying that they fill any open set of the surface, and then they so here two segments. So this is, say, the stable, what am I calling it? Fs, rather. And this is Fu. So U-box is a collection of arcs, all of which begin and end at two arcs of the other foliation. And then you assign a measure to subsets of these things, and to be holonomy invariant is that the measure, so if you take a U-box like this, and you look at the set of points here, the measure that you assign to it here or here is the same. Okay, so that's what holonomy invariance means. Okay, and then to say that the measure is a product measure is this, that for each, so if you have a box like this, so there's a measure kind of measuring the set of intersections of black and red over here, but there's also a measure that measures the black segments, okay, and there's also the mu measure that measures some subset of the white sheet here, okay. So, and to say that it's the product measure over there is to say that you measure it over here, you integrate the sizes of these guys along against the measure on the red thing, and that produces the mu measure of the whole set. Okay, that's what this formula here is saying. Okay. All right. So so I think that more or less covers the definitions. So the mu measure. So there's a probability measure on the surface, which is nice enough. You don't want atoms. You don't want empty space in the surface kind of not being seen by the measure, so you want it to be positive and open sets, and then you have this decomposition of the measure into these things, these two transverse measures, and then so what I'm claiming is that this definition here is the correct now generalization of general pseudo-Anosov or pseudo-Anosovs, and now this class of maps has at least the cardinality of this collection of maps the collection of all measurable pseudo-Anosov maps. Now that is an uncountable family, okay? So I'd like to propose this as the correct sort of piecewise linear constant slope family in 2D, right? And to put sort of that into practice, I should have a theorem, which I don't have, but I do have a conjecture and more definitions, okay? So let me do another definition. So you see, right, so those are the models, and then I would like to have a theorem that says that, well, given some Henon map, say, or given many, C2 or C infinity surface diffeomorphism, you should be able to semi-conjugate it to one of these measurable pseudo-Anosov maps down below, okay? Now, I'm going to say what the semi-conjugacy ought to be, right? So here's what the semi-conjugacy ought to be. So for that, I'll say what so entropy is. But so the definition of entropy, probably all of you know. But in any case, so here's the definition I like to use. So you define n epsilon separated sets. So you have a dynamics. You have an n epsilon separated set is a set which up to the nth iterate of the map, any 2 points in the set get epsilon separated. I mean, they might come back again, but anyway, at some point they get separated, so that's an epsilon separated set. So if you have any compact set, which is not going to be invariant for me, okay, so so you can still count the maximal number of n epsilon separated points you can fit into this compact. Okay, the compact set is not invariant, it moves around, but you count, you put n epsilon separated subsets in it, you count the number of n epsilon separated subsets of K, right? And then you take some lim sups and lim as epsilon go to 0. That defines the entropy of the map F in the compact set K. And again, I don't need K to be invariant for this definition to make sense. And then you define the I want to call the entropy of F in K the maximum of the entropies of F itself in K or its inverse. Okay? So I take a subset, it moves around forwards and backwards, things happen, and then I measure the entropy forwards, measure the entropy backwards, and I call this the entropy of F in K. Okay? And then, all right, so now we're going to introduce an equivalence relation, which is going to be the semi-conjugacy. Okay, so the equivalence relation is this. You call 2 points zero entropy equivalent if there is a compact connected set which contains both and has zero entropy. Okay, so you want the compact set containing those 2 points which forwards and backwards don't grow too much. So that's what the zero entropy equivalence is. And then, I mean, this thing is invariant under the dynamics. So, if you take a quotient by the zero entropy relation, the dynamics kind of projects to the quotient. And you call a homeomorphism tight if there are no continua, which are, well, except for points, which have zero entropy. Okay, so any continuum which is not just a point has entropy bigger than 0. Okay, and the theorem is this: is that so for any C2 surface diffeo, so this equivalence relation you can define it anywhere, but it works well in dimension 2. And the statement is that any C2 C1 plus epsilon C2 diffeomorphism of a closed surface, if you do this zero entropy equivalence on this thing, the quotient space, which might be very complicated in other cases, in the surface case, the quotient is actually essentially a surface, and the quotient map is tight. That is, once you conjugate away these zero entropy sets, anything that you take in the quotient surface has entropy. Okay? So it says here the diffeomorphism is semi-conjugate to a tight homeomorphism of a generalized cactoid. Well, a generalized cactoid is this. Okay, so you start with a nice surface, okay, but there might be entire non-trivial in homotopy simple closed curves which don't carry zero entropy, or which do carry zero entropy rather, and then you pinch it, and then you might have some pinching happening here or elsewhere. But there's anyway, so this is a picture which is much better than the 1,000 words that it will take for me to define this precisely, okay? But there is a definition of such a thing called a generalized cactoid, which is essentially a surface with pinching, right? And then I, this is made to indicate here, I could have pinched a Cantor set's worth of simple closed curves, parallel, right? So you could have a fair amount of, topological complication, but anyway, there's a definition for that. And what the theorem says is that, well, okay, so if you take a C2 diffeomorphism, you do the zero entropy equivalence, the quotient is again a surface, essentially a surface, but actually a generalized cactoid homeomorphism, okay, which has this property that any compact connected set, which is not a point, actually kind of grows either in the future or the past, has entropy. Okay, so, right, so now we get, so let me go back to the statement. Sorry, I haven't been able. So here it says, so you start with some definition, right? And the map has to be multimodal. Then there is a semi-conjugacy. So now the semi-conjugacy itself is quite interesting. It uses the growth number and all that, and it's a clever, very clever kind of proof. I didn't talk about it here, but I did talk about it in the two-dimensional case. But then you can start with this. You can start with the definition of what the multimodal map is, which we don't have in dimension 2, right? So Henon maps. So one of the first things that one kind of bumps against when trying to understand the Henon family is that these are plain diffeomorphisms, right? So then people have looked for analogs of critical points. Lots of things have been done, but it's hard to really get your hands on something and say, oh, this is the critical point or the correct analog to the critical point. Am I right, Pierre? Yeah. Anyway, so I'm not going to go that route. I'm going to do something else because, right, so here is what I'm going to use somehow kind of cut down the class of maps that I'm going to state a conjecture for. So we say that, so take a surface diffeomorphism and take a periodic saddle, somehow kind of cut down the class of maps that I'm going to state a conjecture for. So we say that, so take a surface diffeomorphism and take a periodic saddle. The homoclinic class of this periodic saddle is the set of all intersections of the stable and unstable manifolds. It's a saddle, so it has stable and unstable manifolds. Well, these might or might not intersect. If they don't intersect, well, it's just P. And if they do intersect, you take the transverse intersections of its stable and unstable manifolds and then take the closure of the set. Okay, so that's called the homoclinic class of a point. So here's the conjecture which I'd like to state is this analog of the Milnor-Thurston theorem. So suppose you have a compact surface and a C2 diffeomorphism, and suppose that F has positive entropy, and suppose moreover that there's only one non-trivial homoclinic class. Okay, so there's this classic result of Katox that says that if you have a surface diffeomorphism which does have entropy, then it has to have homoclinic intersections. Okay, so there must be some homoclinic point with an intersection here, so some periodic saddle with a homoclinic intersection. So you take the homoclinic class of that point, and suppose that's the only homoclinic class. Okay? Say it again? Transversal intersection, yes. Yes. Well, if it's hyperbolic, yes, but I'm not requiring it to be hyperbolic, okay? Because otherwise we would go back to the original problem of countability. So I'm not assuming that these guys are hyperbolic at all. Yeah. As the closure, but I'm not talking about basic sets. I mean, this is like a basic set, except it isn't. Oops. Okay, so suppose there is only one homoclinic class, then the tight quotient, so now take the tight quotient, that by that earlier theorem with Miguel, you can take the tight quotient of this, and I believe that the tight quotient is a measurable pseudo-Anosov map. Okay? Yeah. Right. Which one is the right and which one is the wrong, or the left? Sorry, I'm kidding. Yeah, yeah. Yeah. Well, it's a measurable and topological definition. So, it's a closed surface and a homeomorphism of the surface. And then it has all this structure. It has two invariant foliations, invariant measure, the measure decomposes into boxes of these foliations. It's the product of those. One is squeezed and the other one is stretched by this factor lambda. That's right, yes. It's part of the conjecture. Yeah, in fact, the second half, which I haven't read, is that okay, Pierre? Or? Which this, the Borel measure. Well, so the thing is that, these measures on surfaces, they're all equivalent to Lebesgue up to a topological change of coordinates. This is this Ulam, Oxby-Ulam theorem. So a measure, Borel probability measure on a surface which is positive on open sets and on atomic is Lebesgue. I mean, provided you make a topological change of coordinates. So sort of only one. I mean, I could have said that for this definition here. Is that all right? Or? Okay, so the second part of the conjecture is this, that, so part of the conjecture here is that if there's only one homoclinic class, then the collapsing produces a surface back again. In fact, you don't have that pinching. Now, you might have several homoclinic classes, many, maybe infinitely many, in which case then you'd have a measurable pseudo-Anosov again, except that the surface is not a surface anymore, but it's a cactoid. Okay? Then you could have, lots of little pieces which are permuted, maybe, but the first return map to each one of them satisfies the definition above. Yeah.
And the others were
Would be a cactoid. Yeah, because you kind of pinch off the. If you have a little horseshoe somewhere on the surface in a disk, then that pinches off and it becomes a bubble.
A bubble, oh yeah.
So you could have like warts all over.
But it would be the same surface with some bubbles.
Yeah, yeah. Well, you're not allowing any of the two directions to be killed. Yeah. You could have.
You have a surface and
yeah.
one homoclinic class, which is homotopically trivial, and all others are trivial. So
Or trivial, exactly.
Would be the same surface
with lots of bubbles kind of being permuted. Okay. All right. So you could ask if there are examples, right? You could say, well, actually, I've been told that you're not supposed to give the talk without giving examples. So let me give examples to. All right. So and to justify the fact that I'm being invited to come here, I have to say this. Okay. So this transparency is. Okay, so how do you construct examples of measurable pseudo-Anosovs which are definitely not generalized pseudo-Anosovs? Okay? So here's a definition. If you have any map of a space, and assume it's surjective just for simplicity, you can define the inverse limit to be, so this map need not be injective. And then you define the inverse limit like this. You look at backwards strings of pre-images, right? So this is a sequence of points. Each point is mapped to the next under F. So that's the inverse limit space. And then on this inverse limit space, there's a natural map, which is called the natural extension, which just maps, the string, the backward branch, to the backward branch plus 1 point here, right? The image of the first, or the 0th point. Okay? So that's called the inverse limit space and the inverse limit map, or the natural extension. Okay? So here's the theorem, which, so let me read the theorem. So this is the theorem that provoked this definition, or the definition above, rather. So if you start with the 10 family, you could do this more generally, but let me just say for the 10 family, so you start with the 10 family, right? Just like I had the definition, the formula before. So these are non-invertible maps of the interval, and I'm assuming that the slope lies between square root 2 and 2 for simplicity, 2. And then you restrict it to the dynamical interval as usual, and then you take the inverse limit. Okay? So the theorem says the following, that from this inverse limit of tent maps, there is some semi-conjugacy. You can collapse the inverse limit so the inverse limit space to a topological sphere, and this collapsing, or this quotient of the inverse limit space is equivariant, and therefore the tent family, the tent map inverse limit projects to a map, which turns out to be a homeomorphism, and this homeomorphism is in fact a measurable pseudo-Anosov map. Okay? And the surface again is actually a two-sphere. Okay? So the fibers of the semi-conjugacy are all finite. In fact, this is a very mild semi-conjugacy. You just glue some couples of points. Most of them are just 2 points. You just glue them together. And so the inverse limit kind of projects to a sphere, and then the tent map acting on the inverse limit projects to a homeomorphism of the sphere, which has all this structure in it. Okay? So the inverse limit, if you've ever thought about the inverse limits, so so the way to draw inverse limits is like this. You start with the interval, and then you do the map like that, and then you do the map again, and then you do the map again, and then after 4 or 5 times, and if you were a graduate student like I was kind of studying this, then you did like 5 or 6 times, and the pictures became very complicated, but very nice. And then you see sort of the inverse limit kind of appearing in front of you, but it's clearly kind of foliated by arcs, right? I mean, or it has lots of backtracking all over the place, but still. And what you see here is exactly this unstable manifold that I was talking about, or these boxes, okay? And there's another direction, which is sort of the vertical direction here, which produces the other foliation, and then the inverse limit map just squeezes and stretches things and kind of bends them around. And that's what, that's essentially the kind of hand-waving proof of this theorem. The inverse limit is this complicated, foliated thing, but you can actually kind of fit it on that sheet of paper there, and then you glue, pairs of points that are, on top of each other, and that gluing actually produces some nice quotient. The nice quotient is a sphere, and then all the structure is contained in there. It has a contraction factor, expansion factor. The contraction and expansion factor is exactly, the growth rate, the growth number S of the tent map. Okay, so. And okay, right, so this is, this is a theorem, but moreover, you can actually prove that this measurable pseudo-Anosov map is a generalized pseudo-Anosov map by the definition I gave before, that one with those nice foliations where I had actual pictures, is a generalized pseudo-Anosov map if and only if the tent map you started with had a finite critical orbit. Okay, so if the critical point, the turning point of the point, where things break, so if that has a finite orbit, it's either periodic or it lands on a periodic orbit, then the construction produces a generalized pseudo-Anosov map as I had before. Okay? So in particular, now, this theorem here constructs a family of measurable pseudo-Anosov maps, which is, uncountable. Every S now between square root 2 and 2 has, a corresponding measurable pseudo-Anosov S. And this family actually contains a subfamily of, which is countable, of generalized pseudo-Anosov maps. Okay? So,
you need to have two generalized foliations.
Yeah.
One is that one. What is the other one?
Yeah, the other one is red. The other one, it starts life as being the fibers here, the vertical fibers, the points that project to the same point here. So, well, in fact, in the inverse limit picture, the stable foliation is exactly, so the partial stable foliation are the fibers over pi 0. So in the inverse limit, we just look at all points whose first coordinate is pi 0. So that actually, you have to prove that, but that is actually sort of a Cantor set which has an order to it. And then, a Cantor set with an order to it has gaps, and then if you collapse these gaps, that produces an arc. So that's, the proto sort of stable foliation, but then the map actually joins two arcs together if they map on top of each other, so then you produce a global foliation that way. Okay? Yeah. Oops, wait. This or the next? Yeah. Right. Yeah, this is very trivially checked for zero entropy maps. It's true. It's true. The quotient is a point. Okay. Right. Yeah. Well, you see, if I were to be completely honest, I'd say no. But that's not the way you behave in front of professionals, right? So I'm going to give you morphisms as a family, a parametrized family of homeomorphisms of the plane. Now, it's not a family of diffeomorphisms. But it is a family of homeomorphisms. And then that conjecture is true for this family of, and then you have an uncountable family of homeomorphisms for which the zero entropy quotient are measurable pseudo-Anosovs. But they are homeomorphisms, they're not diffeomorphisms. You see what I mean? Well, right. So wait. So I could have given an honest and slightly non-trivial answer that the quotient of Oh, right. So the quotient of this map is a generalized pseudo-Anosov. So if you take the Henon map, right? If you take a what? If you take an axiom A map, for example, you get generalized pseudo-Anosovs. Right. So anyway, it's slightly non-trivial, but if you want diffeomorphisms, then I have to say no. I don't have any non-trivial example whose quotient is a non-trivial measurable pseudo. Well, I think I don't have an example. I'm sorry, but I could think about it. But in any case, so what the family of inverse limit does for you is that it constructs a parameterized family of homeomorphisms whose zero entropy quotients are exactly these measurable pseudo-Anosovs here. Okay. So they are surface homeomorphisms of the plane. But this question of embedding the inverse limit as a diffeomorphism of the plane is very delicate. It's something we didn't need. We're not trying to do diffeomorphisms. We're trying to construct these examples of studying prime ends, other things. Okay, so doing that, and then they're homeomorphisms. So you can't try and make them into diffeomorphisms. But that's not my cup of tea. I haven't tried that. Okay. Anyway, so Tobias got up, so I'm better shut up. Okay. I want to thank you. Yeah, I'll answer questions. Yeah.